Okay, so what I want to ask is, what does it mean when I say factor something? If I say factor 48, what would you do?
Find what goes into 48.
Okay, and pick something. What goes into 48? 12, okay? So when we do a factor tree, you'd say 12, and you'd figure out by dividing 12 into 48, right, what the division of it results in. Agreed? So what if I were to say, for example, factor x to the fourth plus 8x cubed plus 12x squared minus 7x minus 14. And I said factor that. What does that mean? Find what goes into each number or the whole thing? The whole thing, right? In other words, we want to express this sum or difference of products as a product of sums. And when we had 48, we could figure out what numbers go into it easily, pick one of those and do the division, and that's what results. And could this have been just as easily 6 and 8? Or 2 and 24? Or 16 and 3? There are lots of ways you could do it. And you just had to pick what your starting value was, so you would divide it in and get your quotient. You guys with me? So when we divide this, right, we're going to factor it, which means divide it by something that we know goes into it. The question is, how do we know what goes into it? So that's what today's lesson is all about. If you're given a polynomial with a degree greater than 2, how do you factor it? What's the process of identifying what goes into it, and how do you do the division to pull out what remains? Before we do that, let's talk quadratics. In the world of quadratics, we've learned how to do some things. If I gave you this quadratic, look at it, talk to your neighbor for a second, tell me what you would do. Go.
I'll put it in the timer. 10 minutes.
Did my mom just die? You'll get through both pages in the rest of the class, right? Okay. Thank you so much. You want to do it over here? So,
Yeah, I can move my stuff.
Yeah.
All right.
Can someone please raise your hand? Please raise your hand and let me know what you would do with this. Yeah, Jordan. So you would factor it. You guys agree? And you've learned to do that. Like, that's the first thing you do. Why? I agree that that describes the process that he went to find this factorization. But why would you choose to factor a quadratic? Why wouldn't you leave it alone? Good. You can find the intercepts. If I asked you to look at this first one, you can find the y-intercept easily, right? The y-intercept happens when x equals 0. If I plug in 0 for these two components, I'm left with 7. That's easy. But if I want to find the x-intercepts, I have to set the y equal to 0. And if I set 0 equals to this expression, there's just too many possibilities. Adding and subtracting and adding numbers and getting one that matches 0, there's a bunch of them, right? I could do -5 and +5 make 0. I could do -3, -2, +5 make 0. I could do -8, +8 makes 0. There's an infinite number of choices that add together and subtract together to make 0. But if I can turn them into products, it's different. The zero product property tells us if in fact these two multiply to make 0, what must be true? If these things multiply together to make 0, what do you know? At least one of them equals 0. So if this is the part that equals 0, then x minus 7 equals 0. We know that x is 7. That's one of our possible solutions. If x minus 1 were the thing that makes it equal to 0, then x equals 1. That's the other solution. And like you guys said, that gives us, let's see, 1 and 7. Those are x-intercepts. The y-intercept happens up here at 7. We could then use an axis of symmetry to find what it is and graph it, right? Or resolve it in some other way, which depends what we're talking about. If we're talking about, is it face up? Whatever the quadratics are. But this idea of factoring it is super important. What if you get that problem? Do we all agree you cannot factor that? There's no two numbers that multiply to make 1 and at the same time add to make a -8. So what now? Can you factor it still? Okay, how? I mean, we agree that it's going to be something times something. What's the first term going to be here? X and X. What tools do you have at your disposal besides the diamond factoring process? Quadratic formula. Okay. Why does that work? Have you guys ever derived the quadratic formula? Okay, buckle up, Buttercup. Here we go. The quadratic formula allows you to solve for x values from this, right? And you guys remember what the quadratic formula says? What is it? Agreed? This is what we're aiming for. How do we get from this to that? We're going to complete the square. Do you remember completing the square? If you factor this, what happens? You could express this as x minus 3 squared, right? Because the same binomial is being multiplied times itself to make this. It's a perfect square. What if I wanted to find a perfect square that makes this plus some other stuff over here that I can't quite see? Do we know what the first term is? X. Well, let's see. When this was -6 and +9, we had to find two numbers that multiplied together make 9 and at the same time add to make 6. The problem with finding the square root of this is we don't know whether it's positive or negative, right? When you do square roots, it's plus or minus. But I can take half of this. What's half of -6? So what's half of -10? Isn't that the perfect square rendition of this? But of course, if I did this, I'd also have a plus 25. So we can use this idea to solve quadratics that are difficult. Now let's do the one we were doing before. I think it was that, wasn't it? I could solve this using completing the square. Step 1, I'm going to move this to the other side. Step 2, I'm going to express this as a perfect square. What's the first term going to be? I don't even need to write it as 2. I can just write it as a perfect square. I know that's what I'm aiming for. What's this part going to be? When we had -6, it became a -3. When we had -10, it became -5. So if we have -8, what's this going to become? -4. Now, unfortunately, this is not exactly the same, is it? When I take x minus 4 and I square it, I'm going to get x squared minus 8x, but I'm also going to get something over here. What am I going to get here? Plus 16. Now, I've just added that to this equation. That didn't previously exist in here, so I have to add it over here as well to keep it balanced. So by doing that, this whole chunk is now expressed in this, and over here, I've now changed this into a positive 15. Who's with me? 5, I'm right with you. 3, boy, you're rambling a lot of directions today, but I think I'm hanging on. 1, you must have had coffee this morning. Okay, good. I want to solve for x. So I'm going to unravel the onion that's wrapped around it. What do I get rid of first? The squared. So I'll square root both sides. And when I square root things, I end up with what? Plus or minus root 15 equals x minus 4. Now what? Add the 4. I end up with 4 plus or minus root 15 equals x. Those are my two solutions of x. So if I wanted to factor this, what I'd do is I'd say x and x minus 4 plus root 15, and x minus 4 minus root 15. That's the factorization of that. You with me? Any questions on that? So let's use that same idea of completing the square to take this to its solution, right? I just solved a quadratic that we couldn't factor by completing the square. So let's do the same thing here. I'm going to subtract c, and I get -c equals ax squared plus bx. Now, that idea that we used before isn't quite going to work here because we have a leading coefficient. It's always harder with a leading coefficient. So let's just factor that out and make that a non-issue for now. Right? I pulled an a out of both terms. Now I want to express this quadratic trinomial, it's going to be a trinomial, it's a binomial now, as a perfect square. What's the first term going to be? X. How do I find the second term? Half of this. What's half of b over a? Excellent. Plus b over 2a. But when I FOIL this out, I'm going to end up with x squared plus twice this x plus this thing squared. So b squared over 4a squared. And I've now added this to the equation, right? I've changed my balance by adding this piece. That's a weird looking symbol there. So what do I have to do to this side? Add an equivalent amount, not the same thing, because this is being distributed by a. So over here, I'm going to add b squared over 4a squared times a. In other words, this will cancel with the squared there. And so having turned this into this, I still got the a out front. And over here, I'm going to have b squared over 4a minus c. Still trying to unravel to get this x. What do I do to unravel it now? Divide by a. So that's going to give me b squared over 4a squared minus c over a equals x plus b over 2a squared. Now what? What do I do to get at the x? Square root. And when I square root it, I'm going to get plus or minus b squared over 4a squared minus c over a equals x plus b over 2a. What do I do now? I'm solving for x. Subtract this. So I end up with negative b over 2a plus or minus square root of b squared over 4ac minus c over a equals x. It's not quite right, is it? It's not really simplified. Do you remember you're not allowed to leave a denominator and a radical? That's not simplified. You have to rationalize this. Well, before I do that, I better combine these two terms. So first of all, in order to add or subtract two fractions, we need a common denominator. So I'm going to say negative b over 2a plus or minus square root of b squared minus, I'm going to multiply this by 4c over 4c. That's going to give me 4ac on the bottom. So that's going to give me 4ac on the top, and this is all over 4ac on the bottom. Excuse me. I was supposed to get, where'd this come from? Hold on, guys, sorry. This is supposed to be a squared. This is a, right? So I'm going to multiply this one by 4a over 4a to give me a 4a squared. It didn't affect this. This became 4ac over 4a squared. Okay. We're close. Negative b over 2a plus or minus. I'm going to treat this as b squared minus 4ac over the square root of 4a squared. What's the square root of 4a squared? These now have the same denominator. So I get negative b plus or minus square root of b squared minus 4ac all over 2a. 5. I could do that. 3. I can work on that. I think I can get to that. 1. I can't believe you can do that. Okay. Take a moment, talk to your neighbor, and rehash, describe what I did to make this happen. Go.
Drag it down.
I don't think it is. It's not. Yeah.
Okay. So that's a bit of a pause there for a second to have you focusing on that. But where we were going was this idea that it's helpful to be able to turn a polynomial into a factored form so that we can do something with it, so we can graph it, so we can identify x-intercepts, so we can see what kind of symmetry it's got. All those things are going to be helped by this. But we have tools for quadratics, right? The diamond problem, quadratic formula, completing the square, all those work for quadratics. They don't work for cubics. So let's go back to what we talked about a moment ago. How do you factor? You divide by some known factor. So take a look at what I've given you today. And let's make sure we know how to divide. Do you remember how to divide? Long division. So I'm going to express this as 101,952. Actually, I'm going to make sure it's near the top. 101,952 divided by 59. And I need to go through this really carefully. What's my first step? And let me be clear about that. We're asking how many times the whole thing here, 59, goes into this whole thing. It's not just the first part, is it? 59 as a whole goes into this once. And it's going to take up all three of those numbers to get this. Was that a good guess? I don't know. Let's check it. I'm going to take that one, multiply it by the 59, and subtract to see how far off I was. In this case, that's going to give me 42. Since I can't do 59 into 42, that was the right call. But what do I do now? I'm going to bring down the 9. And now I'm saying 59 goes into 429. Well, I'm really interested in the 5 going into the 42 to think about to start. Is it 8? 8 times 5 would be 42, but the 9 won't work. That's too much. So I'm going to try 7. 7 times 9 is 63. 7 times 5 is 350. So 350 and 60 is 413, I think. Make sure of that. Is that right? Thank you. How close was I? So let's subtract it. We get 1, 6, 5. And then again, I'm going to see how many times 59 goes into this. Well, 60 goes into 183 times. It's less than that. So maybe 2. 2 times 59 is 118. So I'm left with, what is that, 47? And then I bring down the 2. So 59 goes into 472. If this were 60, 42 would be 7 times, maybe 8 exactly. That'd be cool. Let's see. Need a new color. Say it's 8. 8 times 9 is 72. Carrier 7, 47. Oh, it worked out perfectly. What does that mean, that it worked out perfectly? Good. In other words, I can rewrite 101,952 as 59 times what? 1,728. In other words, I just factored this number into this. What if I asked you to do something like 1,002 divided by 7? Goes in once, 7. 3, bring down 4, 28, 2, bring down 3, 21, 1. Take a moment, talk to your neighbor. What does that mean with there's a 1? Show me the factored form. So in other words, I could express 1,002 as 7 times what? Is 7 times 143 this? No, it's actually going to be 1 shy of that, isn't it? It's going to be 1,001. So if I add to this, that 1 divided by 7, when I distribute the 7 through, that's going to add 1 more to it, wouldn't it? So what this remainder means is it's 1/7 remaining. Okay? Are we remembering our 5th grade? How do we translate that into dividing polynomials? Well, x minus 2 goes into x cubed plus 4x squared minus 16x plus 8. What do I do first? I want to see how those things go in. And I know we didn't pay attention to just the tens digit previously, but that's more important to us. We want to do this tens digit. So how many times does x go into x cubed? In other words, what is x cubed divided by x? X squared. So I'm going to put an x squared up here because x squared, now let's see if I got it right. X squared times x gives me what? X cubed, that's looking good. I want that to cancel. X squared times -2 is -2x squared. And then to see how close I am, what do I do with these two expressions? I subtract them. So I'm going to change the signs on both, and now I'm going to add. What's x cubed minus x cubed? 0. Good. That's what I wanted. I wanted my tens place, my big important ones gone. What's 4x squared plus 2x squared? 6x squared. Now what? Bring this down, -16x. Now I'm interested in seeing how many times this goes into it. So what I say is this term, the front one, 6x squared divided by the lead term here, x, what do I get? 6x. Positive, so this is going to be plus 6x. How close am I? Well, let's see. 6x squared minus 12x. I want to find how close I am, so I'm going to subtract, which means adding the negatives. My 6x squareds go away. I get -4x. Bring down my plus 8. I want to see how many times -4x can be divided by x. What do I get? -4. So that's what goes up here. -4, -4x plus 8, 0. So I know that this whole polynomial can be expressed as what? X minus 2 times right? This is the factorization of this. I've divided out the x minus 2. And to factor it, I express it with the x minus 2 in there and the quotient, what resulted from the division. 5. I know how to do this. I understand what you're doing. I feel so smart. 3. We did this before. I'm a little rusty on it, but I think I can get back. 1. This is my first time seeing this, and it doesn't make sense yet. Okay, good. I'll leave this one for you to do. What do you do if there's a missing power? You got to put zeros in. So like if I were to write this out, I'd write x to the 4th plus 0x cubed minus 64x squared plus 9x minus 80 x minus 8. You have to put a 0 in for the gap here. Otherwise, your place values don't work. Now, flip the page for a second, please. Do you remember synthetic division? This is great, right? That long division is kind of brutal. It's important to understand the foundation, but synthetic division is beautiful. Do you remember it? So we start off by just looking at the coefficients. So what's the coefficient of x cubed? 1. What's the coefficient of this -x squared? -1. -27, -28. Then what I'm going to do is I'm going to put this little corner over here. And what do I put in there? Almost. I'm going to put in what makes this equal to 0. I'm going to say x plus 4 equals 0, so x equals -4. And then the process for synthetic division is bring this down, 1, multiply, and put the answer here, -4. Add these down, -5, multiply, +20. Add these down, -7, multiply, +28. Add these down, 0. What is this? Excellent. It's the remainder. So it's not part of the answer. It's part of the process to tell me that it's done. And that means I can express this whole polynomial, x to the third minus x squared minus 27x minus 28, as x plus 4 times what? This tells us our answer. This was a cubic, x cubed. And so what has to be here so that the first terms multiply to make x cubed? So this is going to be an x squared. This tells us the coefficient is going to be 1x squared. And then this tells us the coefficient of the next one. So what goes next? Minus 5x minus 7. And if there were a remainder, we would have this over x plus 4. There's not a remainder. This factors perfectly. Are we remembering this? Would you guys try this one now, please? Do number 13, synthetic division. Oops. Now, I know it's been a while, but do we agree this is advanced algebra work? It's nice to have a refresher, but we haven't learned anything really new. Let's do an honors problem. Bottom of the first page. We're given a polynomial of a x to the fifth plus b x to the fourth plus c x to the third plus dx squared plus ex plus f. Find the remainder when you synthetically divide by x minus p. Go. Are you seeing a pattern? See if you got the same answer I did. And then I want you to talk with your neighbor and analyze this. What is it we just produced? What do these letters and numbers mean? Okay. Anyone got an idea? Miles, what do you got? We switched out X for P. True. But what is this that we just created? It was a lot of work, a lot of careful algebra to make sure that we did it correctly. And yes, there's some cool patterns to it when you do it. What's this? What does that represent? Say again? The remainder. Right? When we did synthetic division, what came out as the bottom here was our little remainder thing in the box. So that's what should be 0 if it's a true factor, isn't it? So if you were trying to find out if P were, could you set this equal to 0? Yeah, there's a whole bunch of variables in there. Well, interestingly, wait a minute. How does this compare to this? Do they have any similarities? Switch the X and the P. What does that mean? Let me restate it. We did synthetic division for a P on this whole polynomial, and the remainder gives us a value that's equivalent. Yeah. Yeah. It means that if I just put P in for X and evaluated it, I'd get the remainder. We knew that a 0 in the remainder was important, right? And we knew that, for example, right, X minus 4 times X plus 2 is X squared minus 2X minus 8. Agreed? And what is the X value that turns this into 0? 4. And if I plugged it into the original, 4 squared minus 2 times 4 minus 8, 16 minus 8 minus 8 is 0. That shouldn't surprise us. If we put in the value that's an x-intercept, that forces the y value to be equal to 0. That's what an x-intercept does. That's not surprising. But what is surprising is that if we want to find out what the remainder is, it's the same thing as what happens when we put in that number, the x value that makes it equal to 0, or we hope, for x, even if it doesn't come out as 0. So what does that mean for us? Well, this is called the remainder theorem that we just derived. And what it says, if a polynomial function f of x is divided by x minus c, then the remainder is what? The remainder is the same thing as what would happen if we had plugged in this case, c for every x along the way. F of c. So we can now use synthetic division a different way. We can use it called synthetic substitution. Now go back to the beginning here. Remember when we talked about factoring? It's like undividing, but the trick is you got to know one of the ones that works first. So if we wanted to see if we could factor this, is c equal to -3? Is that the right value to plug in here? In other words, if we did synthetic division with -3, would that work for us? I don't know. It depends on if the remainder is what? 0. And we can use synthetic division to see that. So let's just do that. -3 goes into 1, 8, 12, -7, -14. 1, -3, 5, -15, -3, 9, 2, no, too fast. 1, -3, 5, -15, -3, +9, 2, -6. Huh. What does that tell me? Two things. -3 isn't a 0, an x-intercept, right? X plus 3 is not a factor. And if I did want to find out what this equation was equal to by plugging in -3, the answer is -20. F of -3 is -20. And wasn't that a lot faster than actually putting -3 in and calculating it? Whole lot faster. Go down to the bottom here. The number of tickets sold during an Oakdale high school football season can be modeled by the equation f of x equals x cubed minus 14x squared plus 72x plus 68, where x is the number of games played. Use the remainder theorem to find the number of tickets sold during the 7th game in the season. So I'll give you a choice. You can either plug 7 in for all these x's and do the math. Anyone want to do that just to do a time test? No? You guys all want to do synthetic substitution, don't you? Just put 7 in to synthetic division. $140, $150, $161. This is positive. 229. What does that mean? After the 7th game, the high school football team had sold 229 tickets. Five, I understand how to do synthetic division, how it can be used as synthetic substitution to find the value of f at that function, and the importance of the remainder, whether it's 0 or the value of the function for that x. 3, I watched it, I understood it for a minute, but I think some of those things are leaking out my ears right now. 1, this has been confusing for me. This is a lot. Excellent scores. Nice. Okay. Couple more things. If we want to factor this, what we've just talked about is we can take values of x that we think might be the zeros, might be the x-intercepts, and plug them in using synthetic substitution to do it easier. And if we get a 0, then we know it's a factor. And the beauty of using synthetic substitution is that if it becomes a factor, if you get that 0, you've already got the quotient, the result, as the other part of what you ended up with. So the trick is, what numbers should we test? Like when I asked you to factor 48, nobody said 7 times something, because you know 7 is not a factor of 48. So do you agree that this is going to end up being a product of a binomial, 1, 2, 3, and a quadratic trinomial? And we know that this is going to be quadratic here. We don't know what's going to happen there. This is going to be an x, right? And what do we know about these two numbers, the ones I circled? Almost. When they do what? When they multiply, they have to equal -12, agreed? So won't these two numbers have to be factors of -12? Right? So if I want to find what things are going to work here, I have to pick numbers here that are factors of -12. There might be some other choices as well, but those are in here. So the factor theorem says that given a polynomial, function f of x, comma, x of c is a factor if and only if f of c is equal to 0. Right? We do synthetic substitution and see if it works out to be 0. So let's see if these things are factors. They're giving them to us. Does it work? Well, let's see. F of -6. That means I'd take 3, 13, -32, -12, and I'd put -6 in. 3, -18, -5, 30, -2, +12, 0. So what does that tell me about x plus 6? It's a factor. The remainder is 0. It's a factor. And is -6 a factor of -12? Yes, that doesn't really surprise me. That seems like a good choice. Okay, let's try -2, x minus 2, excuse me, which means f of 2. And what I'm going to do here is I'm just going to lightly cross these out for a second and pretend that they don't exist. So I'll bring down the 3. Multiply times 2 is 6. Add those together. Times 2 is 38. 6 times 2 is 12. I get another 0. See, I'm just saving a little bit of space by not having to rewrite it. So that works also. What about f of -4? Bring down the 3, -12, 7, -28. Oops, sorry, I'm looking at the wrong thing. It's the risk of doing what I just described. 20. No, 25. -12 is 1. -4 is -36. -120, -144 is -156. Not equal to 0. So this one does not work. So once again, we want to remember that if we want to find the factors, there's a couple pieces that we know about polynomials. A polynomial has a degree of n, can have at most how many real zeros? At most. If it's a 4th degree function, how many zeros can it have? 4. So it could have at most n real zeros. And real zeros can be of the form in rational structure, meaning they can be created as a fraction, or irrational. like 4 plus the square root of 5. If we know that we're going to try to cleave off like the 4th degree piece and the 3rd degree piece and get down to our quadratic, and then in our quadratic, we can use quadratic formula or completing the square to get the irrational ones. Let's aim for the rational ones. Let's try to get those first. Rational zeros are those that can be written in the form of a fraction. And based on what we've just looked at, that fraction is one of the P over Qs. You remember this? Did you guys do this in advanced algebra? No? That's what the last class said. I was very surprised to hear that. This is called the rational zero theorem. And what it says is that if I'm going to take any polynomial and find a factor of it that is rational, that has rational zeros, that the only way that works is if the ratio of P over Q is that zero, where P is the factors of the constant. In other words, A sub 0. Like I said earlier, if the constant says -12, then we expect that the factors of -12 could be the values. You want to turn off the lights? Would that be easier? I see you guys all squinting a little bit. We're almost done. And Q is the factors of the lead coefficient because, thank you. Like, let's say this is our quadratic that we're trying to factor. 3x and x, -2 and 1, and it ends up like this, right? So I get 3x squared plus 1x minus 6x is minus 5x minus 2. When I find my zeros, I'm going to get x equals 2, which is a factor of this. But I'm also going to get 3x plus 1 equals 0, 3x equals -1. That's a factor of the final constant term. But I'm going to have to divide that one by 3. So that's why we use this P over Q, where the top is factors of the constant term and the bottom is factors of the lead term. Factors of lead coefficient, A sub n. So let's take a look at number 3 here. I want to find all the possible rational roots. List all the possible rational roots. So I'm going to find my P and my Q's. P is all the factors of this constant term. Tell me all the factors of this constant term. 1 and -1. Couldn't I factor it as -1 times -1? What about the factors of Q? Could be 4 times 1. So factors are 4 and 1. And 2 times 2. So the factors are 4, 1, and 2. Agreed? Now, could they also be -4, -1, and -2? They could be. But I'm about to make a ratio between these two. And so if I were to say, for instance, 1 over 4, that's one of my possible rational roots. And then I'll say -1 over 4. That's another one. Is it worth saying 1 over -4? And -1 over -4? These are the same, aren't they? So in other words, you don't need to do the negatives of Q. You just need to make sure you have positive and negatives of P, and that'll take care of everything. So what's another pair of factors? Good. 1/2, -1/2. Last pair? Yeah. 1 over 1, and negative 1 over 1. These are all the possible factors, including the last one that I just cut off. So if I'm going to see if they work here, I could use synthetic substitution to try them out. And if they work, I know it's a root. I know I've got a root at 0. And I'll know the result. How's that feeling? 5. I think I get it. 3. I'm almost getting. I need to practice. 1. I'm missing something. Okay. So this is what we're aiming for. We want to be able to first list all the possible rational roots using the rational zeros theorem. Then test those zeros using synthetic substitution. And when you find a zero that works, use the remainder to completely factor the polynomial, then find the zeros. In other words, if the remainder comes out to be 0, then you know that you can factor it with that. So let's do our P's over Q's. What's 1? Well, the factors of P are what? 1, 2, 4, and 8. And then the negatives of those. What about Q? Just 1. So this is going to be easier for us. We only have to test these values. Someone pick one. What do you think? 1, okay. 1, 1, 4, 4, -2, -2. That didn't work. -1, 1, -1, 2, -2, -8, 8. That worked. Now, you guys haven't taken a lot of stats, but how many possible rational roots did I have to test? There were 8 I could test. So was my probability here 1 out of 8? Did I get super lucky? No, because how many are there? It's a cubic. So there's 3 out there. I only had to pick one of the 3 that are right. And now that I've gotten one, should I keep going and try 2 and -2 and 4 and -4 and 8 and -8? I mean, you could, but I wouldn't. I now know that this thing can be expressed as x plus 1 times what? X squared plus 2x minus 8. That's a quadratic. We've learned how to factor quadratics. I can do that with my diamond kind of thing, right? X and x, 4 and 2. I want the 4 to be positive, the 2 to be negative. So x equals -1, +2, -4. Doable? Cool. All right. You have the rest of the period to work on this, please.